Hi, everybody, and welcome back. So today we're going to talk a little bit about shop drawings or blueprint reading. So this is obviously a really important skill to have because we need to be able to take what an engineer or a customer is envisioning, what they put on paper, and turn it into a viable product. So if you're going to be taking a CNC operator certificate, you're going to be required to take the blueprint reading through welding. That'll go a little bit deeper dive into symbols and annotations and that sort of thing. But we're going to kind of cover some of the broad basic stuff about blueprints, some of the things you should expect, and how to look at some of those blueprints. So let's go ahead and jump right into it now. So what we should kind of expect from blueprints are drawings that shows machinists what to make, obviously. This is going to be ranging from just an individual part to whole assemblies. We're going to identify some of the standards to follow so that the parts fit together properly. We'll call those tolerances. We'll also identify, the different types of drawings that there are. I think I already mentioned, there's individual part drawings or there's whole assembly drawings, how a machine or some sort of components fit together. And then we'll talk a little bit about the signs and symbols and figures that we use when we're talking in plan drawings. So what types of things should be included in a drawing? Now I want to preface this by saying we're going to see an image of a drawing here in a little bit. And it's very unique to the designer of how the layout of that drawing is. Now we should expect to see all of this information on there, but from my examples, don't expect it to be in the exact same place. Each drafter designer has a different kind of feel or layout to their designs. So you should get all this information, but you might have to dig around a little bit for it. So some of the things that we should expect to see are obviously the material being used. Is this a metal part? Is it a plastic part? What is it that we're working with here? Required surface finish. We'll talk a little bit more about how that's annotated and how we go about finding that out. That's basically what does the finish look like when it's all said and done. Tolerances. That's our acceptable range to be out. We'll talk about that when we talk about measurement as well. Quantity of units. So how many units do we need? Are we making a production run of 5,000? Or are we just making one of them? The scale. So the scale of the drawing is a representation of the actual size versus what's on paper. We'll talk about that as well. Dimensions. So obviously this, we need to know what size something is in order to create a part, and whether or not it's an assembly or sub-assembly and what the instructions are for that. So sometimes, as a machinist, we're asked to just make a part. Other times we're asked to make multiple parts that fit together. So in assembly drawings will show you how those orient together. Are there any fasteners? What should be used in that instance? Past revisions. So this is an important one. Revisions are any changes to the plans. So the designer drew up something. We go to production, maybe we make a unit and we send it back and he says, this hole needs to be a little bit bigger. Maybe we need to change this location. We need some way of documenting that so that we make sure that we're all on the same page, no pun intended. So that when, we're making parts, if we produce a part, get it to the designer and he says, oh, that's the wrong part. Well, what revision are we working on? Oh, well, you don't have the latest revision, Mr. Machinist. So obviously that's our fault. And then obviously we're going to expect to see a name of the object on there as well. So here's a sample drawing, and you can see some of that information listed here. So we have the name of the object down here, and in this instance, in the lower right-hand corner. It could be up the side, it could be on the left-hand side, it could be pretty much anywhere. We have the quantity required, so there's 2 required in this particular drawing. Additionally, there's a drawing number. Now, this could be a completely arbitrary number. There's no rhyme or reason to this except for what the company has put into place. So this is just a reference number that say they built a product 10 years ago and they need to either bring it back in or make some more of those parts. They have a reference number to go back and look at it. Because, imagine you're a bike shop and you make front forks, right? If we made 1,000 different front forks and we called it front fork 1, front fork 2, that might be a little bit hard to kind of pin down which one that we're looking for in the past. So a good, document system for finding out where those plans are is good. Down here we have the scale right here, and in this instance it says full, which means it's it can be either articulated as full or one-to-one, meaning that the size that you see on the paper is a direct representation of what it's going to be in real life. These scales can change a little bit. We'll talk about that here in a minute. We have our revisions up here on the top. So if we look here and we kind of dig around this area, we're going to look for revision A. And if we come down here, there's revision A. Right now it says it's a quarter 20 unified national course, fit number 2 for that hole right there. If we look at the revision, it says it used to be a 5/16 18 bolt. So that was a change that was made and documented. In this particular one, it shows the next assembly. So this would be part of an assembly drawing, an individual part that fits into additional components. So this would be the next in line, the next part that we have to produce. This is our tolerance box right here. Now tolerances, we'll talk about tolerances a little later on, but this is a pretty typical way of kind of generalizing tolerances. Just so that it cleans up the page a little bit when we're looking at the page, so that each measurement doesn't have its own individual tolerance next to it. And you'll see what that looks like in a little bit. And then down here we can see the material being used as well. Obviously, the majority of the time we're going to have some area where we note the drafter or the designer. You know, in a large company, there may be 10, 15 different engineers working on a project. So we need to be able to go back to that engineer if we need any changes made. We have some general notes over here about, you know, just random things like remove burrs. That would be a good thing to do. And break all sharp edges, 10 thou max. And then note that this is a surface finish annotation right here. So 125 micro inches surface finish overall, except as noted. Okay, so if there's a specific area that wants something different. So when we talk about dimensions, there's a couple ways that we can dimension. We can use fractional dimensions. Now this is something you're probably typically see when we're building construction drawings or something like that, or we're building large components that fit together, where we use fractional measurements for that. Over here, we have the decimal equivalent of that. You can see it's the same exact number. Little break here. Do you think this one is more accurate than this one, or which one is preferred? Which one do you think is a preferred method for dimensioning? Okay, so over here we have some positioning information. So imagine that we have a plan and it needs a hole. So if we look over here, we have our hole. This particular spot right here says diameter. That's the diameter symbol. Diameter of 500 thousandths, and then it's going to give us a tolerance right here. It says plus or minus 2 thousandths of an inch. That means that hole can either be bigger, so 502 thousandths, or smaller, 498 thousandths. Anywhere in that range would be acceptable for this part. And then if you look at our dimensioning, it says from this edge right here, we want to go 2 1/4 inches over. Now there's a problem with dimensioning like that, and that's because we don't have what's called a true position, meaning we only have, in this instance, an X location. So that means that this hole could be anywhere along this axis right here. So in order to really identify where a hole should be placed, we need to give it 2 points. We need to give it an X and a Y in order to give it a true position. So here's the same annotation, but we're saying 2 1/4 over and 3/4 of an inch down to the center line of that hole. That gives us a very accurate location to read. We'll talk a little bit later on about geometric dimensioning and tolerances, which actually become even more specific about hole location. Now, and sometimes you're going to see measurements in parentheses like this. This is called a reference dimension. And these are important to note because basically what this is saying is you should have X amount left over, okay, to this other edge. So in this instance right here, we have 1 inch 625 thousandths plus or minus 1 thou from this edge. And we would call this edge our datum point, okay? So a datum point is a feature or an edge that we're going to pull all of our measurements from. And that's a very important thing, is to have established datum points that you measure from, because you can end up what we call compounding our errors or stacking up our tolerances to actually have a part, even though it seems like it fits within the tolerances and all the holes are within the same tolerance, it ends up being out of tolerance completely. So what this is saying here is after we've gone over the 625 thousandths, plus or minus 1 thousandths, the leftover to this edge should be 875 thousandths. Now, talking about stacking up tolerances, the way this works is if we, let me see if I can get a, jumping around here. Let me jump out of this here. And we'll get a, oh goodness, now I can't. There we go. Okay. So if we have a box like this right here, and we want to place a couple of holes, okay? So we have a hole here, and we have a hole here, and we have a hole here. If I have these dimensioned off of a datum point, say that this is 1 inch, and we'll say plus minus 0.002, and then this next hole is 2 inches, plus minus, it's really hard to write on these things, 0.002, and then 3 inches to that hole. Oh, that's ridiculous. Three inches plus minus 0.002. And we'll say that this whole overall thing is 4 inches from side to side. What happens is, if I can start stacking up tolerances, is if I don't use this one reference point, or we'll call this side right here, we'll call that datum A, and it'll be annotated something like this, datum A, okay? You notice how all of my dimensions are pulled from that one side right here. 1 inch out, 2 inch out, 3 inches out. The problem is let's say that I dimension, this would be the right way of doing it. Let's say if I dimension over here and I say from here to here, 1 inch plus minus 0.002. And then I say from here to here, 1 inch plus minus 0.002, and then the same thing over here, from here to here, 1 inch plus minus 0.002. Now, in theory, if everything was perfect, these holes should be in exactly the same place. But what we can have in this scenario right here is a compounding error, or stacking up our tolerances. Let's say that when we did this hole to this hole, we ended up that +2. Okay, so we ended up on the high end of our tolerance, but it's still within tolerance. We're okay there, okay? So this hole right here is plus 0.02 of an inch. Now, we're already starting over 0.02 of an inch. Now we come to this one, and let's say we do that same exact thing, and we end up plus 0.02 of an inch, 0.02 of an inch between this hole and this hole. And then we'll say we'll accidentally do it the exact same way over here, and we're plus 0.02 of an inch between this hole and this hole. Well, now if we measure off this side mark right here, instead of being plus or minus 0.02 of an inch from this edge, now we're over 0.06 of an inch, okay? Our tolerances have stacked up to make us way out, whereas in this one right here, if one of them's out 0.02 of an inch, we have a chance to kind of check that again on the next one. So that's what we mean when we're talking about stacking up tolerances. And that's why we only use a datum, because over here, if we were to say kind of the same scenario right here, if we were to use the distance between this edge and the hole, and then use this datum from this edge to the hole, we can have some tolerance issues between here, because maybe our overall block ended up being 0.02 over as well on this edge right here. So it ends up screwing up our measurements between these holes. So datums are super, super important. So let's go back to our PowerPoint here. And we will continue on. All right, on some plans, you might see what's called dual dimensions. Now, we live in a international economy. And so we're shipping parts across the seas, they're shipping them back. We want to make sure that we're paying attention to what type of dimensions that they're actually using. Now, sometimes it'll be in metric, sometimes it'll be in imperial. That's fine, we know. Other times we'll have what's called a dual dimension, where they actually state both. You either have maybe the imperial measurement, and then in parentheses you'll have the metric measurement. Sometimes there's just a slash, sometimes there's one on top of the other. So it just depends on how the designer tries to articulate that to you. So you have to be really careful with that to make sure that you're using the right number, right? That we're either using metric or standard, and we know that, or that we don't accidentally look at a dual dimension and assume that one of those is one or the other, or accidentally look at the imperial and the next one look in the parentheses and use one of those metric measurements, okay? Because that could obviously screw up our part pretty bad. And we already talked a little bit about metric dimensioning. Just make sure that that is that you're paying attention to that. All right, materials to be used. So sometimes in shop drawings, we'll have what we call a section view, and we'll look at that here in a minute, where basically the designer is trying to show you what's happening on the inside of a part, right? So let's take my coffee cup here. If I'm showing you a view, an angle like this, you can't really tell what's happening inside the cut or inside the cup here. So what I can do is I can visually cut this mug in half and show you what's happening on the inside, right? Maybe there's something in there that would be hidden just from this front view over here. So when we do that, the drafter, designer, or engineer will use some of these hashes to indicate what that material type is. So if I cut this in half, the solid component that you would see would be, maybe, there's no, here, probably somewhere in here, right? A plastic or a glass, or obviously it's a ceramic, but I don't really see anything for ceramic on there. And there's more than this. These are fairly typical. Sometimes they change a little bit, but just know that when you see these hash marks, it's indicating kind of a solid area. So let's look at that right here. So here we have what we would call a conventional view. So this is some sort of component. And you can see here this thick outside line right here. That's our object line, and that's showing the outside dimensions of our part, the outside features of our part. And if you look on the inside here, there's hashed lines right here. Those are hidden lines. So basically what that tells us is that there's something hidden on the inside. There's something going on inside of that, that particular part. Now, if we were to take that part and do like we talked about and sliced it in half, you would be left with this right here. We're actually seeing the inside of the part. Now we start seeing those hashtags where all of this area in hashtags. That's not one of the hash marks. There we go. I'm stuck in 2020 now. So these hash marks right here show the solid component of that part, and we can reference back and see, okay, that's steel that's in there right there. And then this allows the designer to dimension things or show things a little clearer of what happened in the plan. So getting to the topic of surface finishes, we talked a little bit about this. So this quality of finish that we produce as a machinist is super important. And there's some reasons behind that. And mainly it falls down to money, okay? So the finer the finish, meaning the shinier, the more polished the finish, takes us longer to get there, okay? And this is very typical with engineers who have never done this before, never been in the trade before, is they will specify a surface finish that is way more than needed just because they like the look of it, okay? And that way more than needed translates into a lot of hours and time for that machinist to produce that finish. So it's pretty important to be able to talk to engineers and talk to customers and say, hey, is this finish super important? You're asking for a mere finish. What's the purpose behind that? Or is it something that we can do a less surface, less quality of surface, still have the part be functional and save you a lot of money, right? So it's important to understand that. The smoother the finish, the more expensive it is to manufacture. So when we talk about surface finishes, they're measured in micro inches or micrometers. There's a micro inch right there, 0.000001. we can also call it out in what's called a roughness grade. So you saw the little check mark on the previous plan. It was a check mark with a 125. That means 125 thousandths or 125 millionths of an inch. So that would be 0.000125 of an inch. And what we're talking about surface finish is unevenness in the surface. Okay, we're not talking about it being at an angle or parallel. We're talking about roughness in that surface. Now, sometimes that's really hard to find out. So we can use some tools. I'll talk about tools, but I want to talk about roughness grades too. So we talk about micro inches in that little check mark, but there, you also might see a roughness grade, something like N1 through 12, and those like an N7 equates to 63 micro inches, 0.000063 inches. So in order to understand or to measure that, we can do one of a couple things. So we can either use an electronic profilometer or an electronic surface roughness gauge. Basically what these are, there's a little kind of stylus that we drag across the top of our part, and it reads that variation in the surface and spits out a surface finish for us. Now that's for crucial surface finishes. Those tools are not cheap. They're about $1,500 for a really low end one of those. I bought one for $1,500. That was kind of a cheap one, and it was basically broken when I got it. So they go way up from there. But in less crucial instances, you might have something called a surface comparator. And this is something we have in the shop, and this is something we'll use in the shop when we're manufacturing parts. It's basically just samples of different machining processes. So turning on the lathe or vertical milling, horizontal milling, surface grinding, all different types of processes. And then there's a sample of each of these different roughness grades. So an N7, smoother surface, and N8, and you can start seeing the difference between those grades. And basically what you do is just hold your part up next to it and say, okay, I'm roughly in that area. And that's what we'll use in the shop. So tolerances, we talked a little bit about tolerances. They're the dimension that something can be out and it still be okay. This is done for interchangeability of parts. So we have a bracket and it needs to meet up with a bolt pattern on the other side. Obviously those holes aren't in the right location. The bolts aren't going to fit in. So we need to be able to specify just how far those bolts can be out or those holes can be out in order for this part to still work as designed. So those are our tolerances. Now, sometimes we talked a little bit about that tolerance chart, and I'll show you kind of what I mean by that. This is what we use in the shop a lot. But tolerances can be expressed in a number of ways. They can be done in decimal or fractions. Just depends on how much leeway do we have, right? If we're building in construction, we're fabricating something. A 1/16 of an inch, an 1/8 of an inch might be perfectly acceptable as a tolerance. So we can use fractional annotations for there. We can also have what we call bilateral and unilateral tolerances, meaning bilateral tolerances, it can be plus or minus, and that's what you saw earlier. So it could, instead of being exactly a ½ an inch, it could be 498 thousandths, or it can be 502 thousandths. Anywhere in that window would be acceptable. There's some areas that we have to have what we call unilateral tolerances, means that it can only be one way. So it can either only be bigger than the stated number, or it can only be smaller than the stated number. And here is what I mean by that. So let's say we have a pin and a hole, right? So if I have a hole and then I have a pin, and that pin has to sit in that hole, that's a really ugly pin there, isn't it? Drawing with a mouse is not very good. Okay, that's somewhat better. All right, so let's say that we have a 0.500 and we call out a plus minus 0.002 for this diameter of the pin, and we'll say we use the same thing for the hole, right? Now, full disclosure, you would never do this in real life, because even if they're exactly the same, they won't fit together. That's kind of an interference fit. So one of them has to be a little bit smaller than the other, or the pin has to be a little bit smaller, or the hole has to be a little bigger. So if we did this, the problem with this scenario is, let's say I drill this hole and it comes out to be 498 thousandths. 498, okay, is the diameter that I actually produce, right? It's within tolerance. It's -2. That's still within tolerance. That's fine. And let's say that I have this pin, and I created this pin, and it came out over, and it came out 502 thousandths, okay? Still within tolerance according to our chart right there, but these will not fit together now. Now there's 4 thousandths difference in between these two. The pin's larger, it won't fit in the hole. It won't slide in there, okay? So that doesn't work. So what we can use is we can use a unilateral tolerance, meaning that we'll say on this one, we can only be -2 for the pin, and over here we can only be +2 for the hole. That means that at any point in time, as long as we're within those tolerances, this hole is either 500 thousandths up to 502 thousandths, or this pin is either 500 thousandths down to 498 thousandths, meaning that no matter which way you slice it, the pin is smaller than the hole, and it'll go in there. So you'll see that being used a lot in drawings like this. Now, sometimes you're going to see a chart, and you'll see this on my shop drawings, and you saw this on the other one, which is kind of a key for tolerances. So when we look at shop drawings, right, there's a lot of dimensions and stuff that are going on there. And we want to, when we're drawing drawings, we want to give the machinist all the information that they need in order to create the part, but we don't want to give them more than that. And why do I say that? The reason I say that is because if you look at some of those shop drawings, they get really busy real fast with dimensions all over the place. So I need to be able to look at this and say, hey, this is a crucial measurement. I need to give him that one. This one maybe not a crucial measurement. He can determine that measurement based off of these other measurements and just leave that off the plan. That way the plan is a little bit cleaner. It's easier to read. There's not so many, crossing lines and measurements and stuff that are going to make my eyes go cross. So one way that I can do this is you saw me noting, a diameter of 500 thousandths and plus or minus 0.002. Well, that takes up valuable space on our plan. So what we can do is we can have a key, and we can say on that key, we can say, okay, so for tolerances, we can say x, let's see, period, x equals 0.002. Now this only works if we have some standard tolerances, and we can always note tolerances for a specific dimension. If there's one thing that has to be like a unilateral tolerance or something like that, we can specify that on the sheet, no problem, kind of as noted that everything else falls under this kind of key, and then this specific one needs something a little bit different. That's perfectly acceptable. But kind of for general stuff, what we can do is we can do a key kind of like this. And this is what you'll see on our tolerance sheets. And basically what this key says is that I note the dimension with 3 decimal places, then the tolerance is 2/1000ths of an inch. If I express the dimension in 2 decimal places, then the tolerance is 10/1000ths of an inch. If I express it in 1, then it's 100,000ths of an inch. So if I'm on the this hole back here, and I just say, let me erase this this tolerance right here, and I say diameter of 500 thousandths, well, I can look at my key and say there's 3 decimal places. So this right here would be a tolerance of 2/1000ths of an inch. Or if I said the diameter is 50 thousandths, oh, there's 2 decimal places. Now I have a tolerance of 10/1000ths of an inch, okay? And the same with this right here, 1 decimal place, 100,000ths of an inch. So that's a way of kind of cleaning up and making it a little easier for you to look at those plans and just reference those tolerances. Let's go back here and let me clear my annotations here. Okay, so obviously, number of units and parts that we need to assemble should be listed on there. Sometimes they are, sometimes they aren't. There's companies that produce the same part over and over and over again. You know, they have a line of products that they make, and so they might not give you a plan and say, I need, you know, it might not have 500 on there. They just say, hey, run 500 of these. So not all of them have that. So total units, this gives the opportunity for the facilities to order the correct material and how much they need and determine costs and stuff like that. So scale of drawing, we talked about a little bit earlier, but scales of drawings can be represented in, you know, if you're familiar with architectural drawings, you know, 1/4 inch equals 1 foot. Stuff like that is pretty common. In shop drawings, you're going to see this ratio 1:1, 1:2. So basically a 1:1 drawing is that the size on the paper is exactly the size that it is in real life. So if I need to cut that down, I can have, you know, a 2:1 or I'm sorry, a 1:2, which means that the paper shows half the size of what the actual part is. Or I can say if I want to, it's a small part, I want to blow it up, it could be a 2:1 so that the paper is 2 times larger than what it is in real life. And the reason this is important is not all the time do we have a part that we can draw and fit onto an 8.5 by 11 sheet or even 11 by 17 or even bigger. Sometimes we have to kind of shrink that part down on the plan so that the machinist or whoever's making this has an understanding of what it is they're supposed to make, can see all of the components and all of the features of it, but we've shrink it down so it's manageable and we can see that. That's why, you know, in construction drawings, you know, you draw a house. Well, obviously you're not going to get a paper as large as a house and draw that on there. We need to shrink that down. And so, you know, 1/4 inch equals 1 foot. So we can look at that drawing and we can measure out 1/4 of an inch on the paper. Oh, that's 1 foot in real life. So scales, you know, scales are super important. It's super important to know what scale that you're working in, especially if you're trying to take measurements off of the sheet. Now, I would say that if it's a good drawer, a good draftsperson or engineer for shop drawings, that sort of thing, we shouldn't have to necessarily scale off of the paper, but sometimes that happens. And in order to, you know, if we know that scale, we're able to do the calculations and figure out what it should be in real life. So now we get down to some important stuff, the lines, okay? So there's different lines that you're gonna see on a set of plans, and they mean different things, okay? So the first one that we're gonna look at is the object line. Now this is just the outside line of your part, okay? So what does that periphery look like? This is where, you know, a lot of your dimensions are gonna be taking off of and stuff like that, just a solid, thick line. Inside that, we already looked at some hidden lines. These are these dashed lines right here. So those are going to indicate that something's happening below the surface that you can't see. Center lines are a long line with a small dash in between. You'll see this if we have like a cylinder or something like that. They might put a center line down the center so that maybe they can pull measurements off of that center line or just indicate the center of the part, center of a circle, that sort of thing. Next, we have these phantom lines, and the phantom lines are used to do a couple things. One, they can show how another component interacts or assembles to this, or it can show movement as well. What do I mean by that is, let's say that we have, you know, a widget here, and there's going to be another widget that attaches to the side. We might use some phantom lines to show that extra widget and how and where it attaches to the side. So that's one use of the phantom lines. Another use of the phantom lines is to show movement. And so let's say we have our widget here, and let's say that there's an arm on here that swings like this, okay? And I can show you the solid component, how it fits together, and then I can use those phantom lines. Oh boy, this is getting real bad. To show you movement of that particular arm and say, hey, this arm swings around this way here. Okay, so that's another use of a phantom line. Dimension lines are just thin object lines, basically. You'll see these, they'll either be ended with, usually they have what's called a leader line. So if I have a box like this, the dimension line is gonna have a leader line, which comes off of that whatever feature I'm trying to measure. It's a thin line like this. And the majority of the time, there's a space in the middle with a dimension or something like that. So that is a dimension line. Sometimes you'll see arrows. So if I'm on the inside here, I can't really take a leader line out to the outside. So what you'll see is you'll see something like this comes in and then arrows and points to that corner right there. It says, hey, this line right here to this line is 2 inches. All right, next is the cut plane. So this goes back to that, that section view that we were talking about. Typically, those section views are going to be in another area of the plan. So how this works is we have our widget right here, and we'll take that cut plane and we'll say, maybe we have some hidden features in here or something like that. We'll take that cut plane and we'll do something like this, and we'll call it maybe A, and we'll go this way. And basically what this reference is that if I were to take this piece and cut it in half along this line, like this is my knife, and I cut it along this line, and then I were to open that up, that's where I would go over and I would see my section view, and that's the view that I would see. So you're able to get a reference, an orientation of where that section view is coming from. Okay, it's cutting it this way, and I'm looking at it that way. We talked about the hatching. So obviously this shows a solid area. And then last but not least, the break lines. So break lines are for us to kind of shorten up a part. So we talked about scale. So let's say that I have a pipe that I'm doing, and it has like a special flange on one side, and that pipe is 27 feet long. And then there's something happening on the other side, okay? And I need to show you this part, okay? Well, 27 feet long, I would have to take, in order to fit on this, the paper, I would have to scale it down really, really small in order to get 27 feet on that piece of paper. And when it gets scaled really, really small, well, then it's hard for me to show you the detail and stuff that's happening over here. So I can do a couple things. I can show you either a cut section, or maybe I can just show you a view of just this area right here. Or what I can do is I can add in what's called a line break. And basically what a line break is just tells us that it doesn't change, okay? So nothing changes for in between these two line break sections. So I can draw my flange here, I can put a short piece, and I can say, hey, this is a line break, and that comes out this way, and there we go. And basically what it's saying is that in between here and here, in between this section, nothing changes. So I can denote this by saying 29 feet, 29 feet, and we know that that just goes unchanged in between there. There's a couple ways that you can articulate that as well. Okay. So additional information that you might find on your plans are going to be your assembly, sub-assemblies, right? So we talked about how components fit together and stuff like that. Sometimes you'll be given an individual part sheet. Other times you'll be given a sheet that has both the parts and the assembly on there. So how build all the parts, and this is how it goes together. We already talked about revisions and obviously the name of the part on there. So types of drawings used. So we talked about detailed drawings and assembly drawings. This is what we just covered. So sometimes there's going to be a part drawing or detailed drawing just for a specific part, and then how they all go together as an assembly. There's different sizes of paper that are kind of recognized in design work. The conventional sheets are lettered A through E, and they correspond with a paper size. So an A size, this is an ANSI A size, is 8.5 by 11. A B size 11 by 17, and so on and so forth, up to an E, which is 34 by 44. So this is something that's going to be either a large part or maybe a larger assembly to show things how they go together. There's also a metric equivalent to that as well. So they're the A and then numbered. On some assembly drawings, you might find a parts list, and a parts list is just that. It'll show not only the components, so we need part A, part B, and part C, and we're going to put those together, but it'll also show we also need these nuts and bolts and gaskets and this and that and the other thing, so that when you're getting ready to assemble these, a parts puller or somebody can grab those parts, have them all put together so that we can make that final assembly. We talked about datums. So datum point is a point that we're going to reference all of our dimensions from. And that could either be, a particular spot, maybe a hole, maybe a bored hole, maybe it's a boss, something that's sticking up. It could be a plane, so, a flat face. It can be an axis, X, Y, and Z. Really, we can use almost anything for a datum point. the designer is going to kind of come up with where he wants everything in reference to when he's doing that. So we can also, datums can also be on a feature, and a feature could be anything like we talked about: a surface, a pin, a hole, a slot, something like that as well. Typically, when we look at datums, they're going to be annotated like this. So you'll have, let's say we have our box. We already kind of drew this here. We'll have our box, and we'll say from here to here, this is datum A. So that means that any dimensions going this way are going to use datum A. We're going to be using datum A. And then I might have something down here that says datum B. And so that is any measurements going this way up and down are going to be measured from datum B. So if I have a true position, let's say I have a hole right here and I need to position that hole, I'm going to have a measurement from here to center line, and I'm going to measure from here to center line, okay? Now this is really important to maintain these datums, because what I don't want to do if we're trying to make a component that fits together is I don't want to just start using edges at random because there's free space. So what I mean by that is if I have a hole over here, I don't want to say, oh, it's closer to this edge, so I'm just going to give a measurement from here and from here, okay? That's not using our datum points, and then we can have those tolerances stacking up. So in this instance, I would give a measurement from here and a measurement from here in order to give a correct true position. Okay, so we're not going to go really into this. This is what's called geometric dimensioning and tolerances. This is a more deep dive into positioning features and locations and hole locations to be even more accurate as far as, you know, over a true position. So we're going to cover, I'm just going to go over kind of some of the features that covers. Oh, here we go. Okay, so some of the features that it covers, here's some of our datum symbols as well. This is what a feature control frame would look like in geometric dimensioning tolerances. So it tells us what it is that we're actually measuring for. So that's the characteristic for perpendicularity, okay? And then it's giving us a zone. There's a lot of different stuff that goes in here. Material condition symbols, maximum or minimum material conditions, and our datum reference points, stuff like that. It can get a little bit cumbersome. But let me show you kind of what geometric dimensioning tolerances controls, so you can get a better understanding of how it might be used. So we can control things like flatness. Now this isn't necessarily surface finish, because surface finish is just kind of the cleanliness of the top and how you know, rippled the top is. When we talk about flatness, we're talking about over an overall length of area, just how flat it is. So this is the symbol for flatness. And this is saying flatness is within 5/5000ths of an inch. And so basically what happens is we take a tolerance zone of 5/1000ths of an inch right here on the top of our part, and our flatness has to fall within those parameters. We also have straightness. So this is the symbol for straightness right here. And you can see it's not flatness. It's basically from one end to the other. You know, if we were doing straightness and flatness, we would have, you know, ripples in here as well that we would be measuring along that tolerance zone. But this is a tolerance for flatness, and you can see that tolerance zone here and how the part would need to fit within that tolerance zone. Circularity. So here's our circularity call out, 5/1000ths of an inch. So you can see here's an indication of a section view right here. So it's basically saying if we cut that right there and we looked this way, this is what we should see. And this is our you know, major diameter of our part, and then this is our tolerance zone right here, and you can see the irregularity in there. Cylindricity, that is basically the overall you know, cylindrical component of our part. So rather than looking at a cross section, we're looking at the side of our part, overall length of our part, and there's our tolerance zone for that. This is the symbol for cylindricity. So there's a couple things that that we can't. I think I might have taken it. Oh, here we go. There's a couple more here. Angularity. So you can see how this would work. You know, angularity of a hole, if it's at a certain degree, there's our tolerance zone for that. Or a face drawing, you know, something like that, there would be our tolerance zone for that. Perpendicularity. So 90 degrees, that's perpendicular, right? So there's our tolerance zone for that. There's our perpendicularity call out. Parallelism. So you can see here it's saying parallelism to within 5 thousandths of an inch from datum A. So here's our datum A, and it's saying it has to be parallel within 5 thousandths. So here's our flat datum A, and we're looking at that tolerance zone right there. Runout and circular runout. Now this is an interesting topic to discuss because circular runout we can actually measure, total runout we cannot. Okay, so I don't think I have a illustration of this, but basically circular runout is if we take a cylinder and say we put it in the holder like a chuck, right, and we spin that circle or that cylinder. Ideally we want that cylinder to be perfectly cylindrical to where it doesn't jump around like this. Okay, we want it to spin just perfectly true with the axes of the lathe. Okay, well that's not always the case. Okay, there's always going to be something that we call runout, and I'm going to talk about runout when we talk about the lathe as well. And that is basically kind of this out of round, and it might not be your part, it might be the chuck, but it could be your part. So what we're doing when we measure circular runout is we're taking one point around the circumference of that circle or that cylinder, and we're measuring that. Okay, so we'll take what's called a dial indicator or plunge style dial indicator. We'll put it on there, and we'll watch that thing bounce around. Okay, and that measures our circular runout. Total runout is the overall measurement of each basically individual slice of that cylinder all the way along the length of that part as it's spinning. And there is no way for us to measure that. We can measure it in multiple locations and get a better idea of our circular runout of the part. But total runout, it takes a very, very specialized machine. Mitutoyo makes one. It basically takes and spins the shaft and takes a probe and just runs it up and down and up and down and up and down as that thing's spinning around to get basically every datum point on that or every position on that cylinder measured so that they can determine total runout on there. And you'll see guys that'll say, you know, oh, we measured total runout. I would venture to guess that they did not measure total runout. They measured circular runout in a couple different locations. So yeah, here the entire surface must lie within the tolerance zone for total runout, and we can't measure that effectively. Okay, so last but not least, let me just leave you with a couple of symbols that might have changed on a set of plans, you know, some different ways of doing things. So when we talk about radiuses, so that's basically this radius around the corner, right? Half the diameter of a circle. Radiuses are measured from endpoint right here, and then we have a radius around. Those are illustrated on a set of plans as R by the dimension right here, okay? Diameter, we already talked about the diameter symbol right there, the circle with a line through it. That's how that is illustrated. Old school way of doing it was the number followed by an R for radius and then a DIA for diameter afterwards. So they just cleaned that up a little bit. Here's some ways of articulating some different measurements. So this would be for a counter bore. You can see a counter bore here. Which has a flat bottom to it, and then either a through hole or a blind hole that goes all the way down. Basically, two different diameters. This would be used for a bolt head or something to sit down below the surface so that surface was smooth. So this is what it might look like on a plan drawing, and this is how it would be called out. So that inner diameter would be 500 thousandths of an inch. So that inner hole would be a ½ an inch, and this is stating through, so all the way through our part. And then this is the symbol for counter bore right here. So we're going to counter bore to a diameter of 1 inch. That's his outer diameter here. And this is the depth symbol. So down 190 thousandths. That means that this depth from here to here is 190 thousandths. This is a way of doing it, kind of the old school way. 90% of the time you're going to see it this way now. Countersink symbol. So countersink, we're going to do countersinks in order to flush up the top of a machine screw or something like that. Same concept, 500 thousandths diameter, down 560 thousandths. That means that this center bore does not go all the way through like it did in the previous one. It just goes down to 560 thousandths. There's our counter bore symbol, and to a diameter of 81 thousandths, or 810 thousandths, excuse me, at a angle of 90 degrees. So this would be a specific tool. We use a 90-degree countersink, and we would go down to the diameter of 810 thousandths. Last but not least, we have our drill, which would be our counter drill. So, countersink, wide angle, 90 degrees. We're doing that just at the top. Counter bore is going to have a flat bottom, and a counter drill is basically just drilling on top of another drill hole down to a certain depth. So we have in this instance, our diameter 500 thousandths through. So we drilled all the way through the part with a 1/2-inch drill, and then we've counter drilled. We've taken a 3/4 inch drill and we've drilled down 370 thousandths. So the difference between the counter bore and the counter drill is drills naturally have either 118 degree or 135 degree included angle at the tip. So you can see that there's going to be a little bit of an angle in between those two mating features there. So it's not going to be a perfectly flat bottom like a counter bore will, but it'll allow us to drop something down on the inside there as well. So I hope that gives you a quick understanding of how plans are read. We'll be using these symbols and kind of techniques in class to read the plans on the parts that we're going to draw. They're very simple, but you should be able to make them out. If you have any questions, feel free to contact me, and I'll look forward to seeing you in class.